Welcome to the Crazy Wisdom Podcast. I've got Peter Schmidt Nielsen here, and he is making an FPGA accelerated server at Saturn Data. Welcome to the show.
Hi, yes, thank you for having me.
Yeah. So it's so interesting. I did a call like a year ago with somebody who was making FPGAs, and I had no idea what he was talking about, which is usually a good sign for me that I had to kind of dig in. And FPGAs have started to show up everywhere. I don't know if it's just because I've started to think about them more, so now they're starting to show up everywhere. But I saw a video of yours a few months ago talking about them, and I was like, okay, well, there's another thing I don't really understand, so let's try to understand it. Why does a server need a FPGA? What's the relationship between servers and FPGAs?
Yeah, I mean, it's a great question. A lot of people have tried to sort of make FPGA accelerators for servers. There are, of course, the Alveo cards from Xilinx are one of the most popular examples of this. I think, in general, probably the best starting point is some common misconceptions about FPGAs. So the first thing I'm going to say, which is probably a little bit surprising, as somebody who's doing a whole startup based around FPGAs is that in many ways they really suck. Like I think a lot of people end up quite disappointed by what they can do. Like they think, wow, this is this, custom hardware that I can, customize. It's like an ASIC, but a little bit crappier. But the ratio there is enormous. I mean, the gulf is just huge. You'll find people who are not aware that like, you take some mid-end FPGA and you try to put like a little RISC-V core on it, and maybe you close timing at like 300 megahertz, and you compare that and say, wait a moment, this is giving me like comparable performance to this like, dinky little $2 microcontroller. Like they really are quite niche. So if you want to use an FPGA, you probably have one of, stop me if I'm going on too long, but
No, no.
if you want to use an FPGA, they're kind of, from my perspective, two main reasons. One is you have some sort of latency budget requirement that makes it so there's no other choice. This is sometimes the case in sort of high frequency trading applications. And the other is that you have some sort of I/O requirement where you have no other choice. Like if you want to talk to 1,000 different pins and do some very intricate timing between all of them, be like, oh, I'm doing some crazy data acquisition application. I'm in some wacky lab and I'm receiving at like 800 megahertz on 1,000 wires in parallel. FPGAs are probably, if not your only choice, one of your most effective choices. So there's been a long history of massive disappointment with trying to accelerate real workloads on FPGAs because it turns out that if you just want to do something computational, general purpose CPUs and now GPUs are pretty incredible. Um, so there are various companies and startups. There's a long series of sort of, I don't know if you want to say like a graveyard of companies who say, we're going to put FPGAs and we're going to accelerate your database. We're going to accelerate this, we're going to accelerate that. I think I tend to be in general pretty skeptical of a lot of that, having used FPGAs. Not, as much as you can find plenty of people on Twitter have used them more than I have, but I'm not a complete beginner. Um, you really need to find something that works to their strengths. Now, having said all of that, and said that FPGAs are, in many ways pretty anemic, um, I am putting them in servers kind of more for that second role as the like, you want to talk to a lot of I/O. Well, what is the I/O you want to talk to? In my case, it's DRAM and flash. So the core thesis of my company is that there are a lot of applications that want to have really large working sets. They want to have a lot of memory bandwidth to, a lot of memory and do some sort of operation on it, for which using FPGAs basically as I/O expanders is pretty cost effective. They're a relatively cheap way to get a lot of memory bandwidth and in particular bandwidth to flash. So in a 2U enclosure, we're putting about 1.3 petabytes of flash, and most of them usually we're going to have about a terabyte a second of read bandwidth for that flash. Right now, we're mostly talking to sort of vector database and search companies. There are a lot of potential applications, but I think vector database and search are really well suited to this, to our particular architecture, because you get a huge amount of bandwidth to flash with gajillion IOPS because you have a ton of parallel NVMe interfaces. So that's sort of like the high level. I guess I a little bit rambled there.
really interesting stuff related to DRAM and flash and memory bandwidth. And there's a whole bunch of pins and vectorized databases. You said the memory, and we got to talk about the memory now because the memory is there's now a huge bottleneck. Is this affecting you about like
Uh,
everybody's buying memory because of the GPUs and such?
yeah, a substantial fraction of my bomb costs basically just doubled overnight, which
Oh
sounds
man.
pleasant. Yeah. I will say though, there is a sense in which there's a silver lining, which is insofar as my server is expensive because of FPGAs, if the ratio shifts in a direction where everyone has to pay more for DRAM, the premium I'm paying for FPGAs has comparatively shrunk. So there is also a silver lining.
Okay, so and I want to understand more on the server stuff. And I'm not a heavy duty technical person. I guess I'm a technologist who now can build applications only because of AI. I'm not coding anything, but I do like studying all this different stuff and understanding how it all fits together. But I don't have any hands-on experience. So actually, this is really interesting because I now do a lot of study of technical concepts on Anki, and I asked AI, what are all the different types of servers that exist? And it told me there's web application servers, there are like front end servers, there are back end servers. Like in a large application, you have like thousands of different servers, all like focused on all these different things. And I guess it's also because you need a bunch of servers all over the world if it's a global kind of company with like serving all these things to people in all these different places. Is that an accurate representation of all the different servers that exist in sort of big applications?
I guess it's interesting. There's sort of a distinction here between are you talking about different servers from a hardware perspective or different servers from the sort of application perspective? Because people do, of
Oh,
course, specialize their hardware for the application, but not quite as much as.
wait, can you go more into that? Why do they do that?
Well, I mean, so if you go on AWS and you say, "Hey, I want to give me a box, I'd like to rent it," they'll say, "Well, here's a high memory box, and here's a box that's optimized for this, and here's a box that has an accelerator, and here's one that just has networking and whatnot." So there's sort of that perspective of different servers, and that's kind of where I'm coming in, is saying, "I'd like to give you a different point on this Pareto frontier of if you want this much bandwidth and this much compute and this much whatever, I can, help you out." And then there's server from the other sort of perspective of like, I have my backend server and I have something that's, stripping off TLS, and I have some server that's managing some, front end web serving element of it or something. Like those are, I would say, two separate notions in which you might have a variety of
Yeah.
servers.
So it's a nomenclature, a faulty nomenclature for all these different things that are getting kind of clumped together. And so you're more on the actual hardware. Okay, I got it, got it. And so, what are the things that you're serving, or what are the things that you're helping your customers serve?
Yes. So the main thing that we are starting with is sort of search applications because they tend to have the sort of sparse access patterns that work relatively well for our hardware. I mean, frankly, nobody can really beat the cost effectiveness of GPUs if you just want memory bandwidth per dollar. But if you have a sparse access pattern where you're saying, hey, it's actually pretty useful to me to have a petabyte of stuff that I have sort of terabyte per second bandwidth to, and I'm, going to answer a query, sparsely access some subset of it, then we can help with that. And that it turns out to be a pretty good fit to a lot of sort of vector database and search applications.
Got it. So this is for vector databases. Okay, this is something I've lightly studied. Basically, I remember Pinecone was really popular about 2 years ago, and that's sort of a vectorized database. But then a lot of them actually like what is it? Why am I blanking on the name? Not SQL, but no, PG Vector. PG Vector. Yeah, they enabled that, and that's what I started to use. I've now built a few vectorized databases for my applications in order to do natural language searching, which is really just blown my mind. Is that because as I mentioned, I study a lot of things on Anki, and now to search on Anki is ridiculous because I have to search by keyword, and if I miss one, apostrophe, it doesn't show up. But then I compare that with something like, the craziest thing is that all the LLMs also have not started doing embedding all the chats. So you can't search through all the chats with semantic search. You can't. It's only semantic search. It's only keyword search in all their chats, and it's only I think by the title too. They haven't actually like done the embedding so you can search through all of your knowledge to actually find that natural language. Yeah. So what it like? Why this application? Why are you focused here?
The main reason, just perfectly honestly, is that it's a good fit for our hardware. I mean, I wish I could tell you the story is I have some deep belief in, vector databases, and I think they're, I think they're pretty cool. I think people are doing a lot of really cool work. But it mostly is just a really good fit to our hardware. There are probably other sorts of applications that are sort of more like the full text search that you were just talking about the problems with that were probably also a pretty good fit for. Um, yeah, no, I know what you're talking about. For sure, I have been a little bit surprised the extent to which these sort of LLM apps don't say, "Oh, okay, I would like to now, have every chat I've had in the past as if not literally something that I'm now querying you about, like at least you have some summarized version of that I can then, I do think there's a little room there. I'm sure the companies will fill it in. I mean, they have so many project managers now who are trying to, you know,
Well, that's
but
probably the one
yeah,
blocking them now because they're too big. They've got too many project managers. They got too many coordination costs, and so they're sort of failing to be able to move fast. Like because it seems like it's like such a glaring knowledge management problem. I am a knowledge management profession. That's what I study. So actually, it is really interesting that you are focused on search because I've thought so much about search, which is just that it's the needle in the haystack problem
yes.
where it's like you need to know what you're looking for, but you also need to know like it just show what philosophically what have you learned about search from building these hardware because it's such a giant problem that's always existed for humanity because it goes back to ledgers, right? It goes back to
Right, right.
like ledgers are accounting and they do that because and then that's the in the 1980s the rise of the PC. Those were the first software was built with spreadsheets to keep all this stuff organized, right? What have you learned philosophically about search with these FPGAs?
That's an interesting question. It's funny because I am so zoomed in on trying to make the hardware work, and my day to day is like, oh, I'm getting too high of a bit error rate on this memory interface.
Yes.
So no, I power delivery issues. And so philosophically with search, it's funny. A lot of it really is about just sort of figuring out your access patterns. Like, to a surprising extent, I can estimate the performance that I'll be able to provide for somebody, either a big win or a small win, or maybe it's not, just from the sorts of access patterns they have. Like, when I
What
think about bucketing, sorry, go ahead.
what is an axis problem or a
Sorry,
pattern? What is pattern?
access pattern. Yeah, so if I'm thinking about bucketing potential customers that I'm talking to, I'll think, oh, okay, these are the sorts, these guys are going to want to do a gajillion tiny little scattered reads, and these people are going to be reading big, 10 megabyte chunks, and they're only going to be touching 10,000 different spots for some sparse access, and oh, this person is just going to do one big sweep. And uh,
Mm.
probably some of what I'm saying is because you're talking to a hardware guy, and if you were talking to somebody at Pinecone, like you mentioned, or any of their many competitors, they would give you a story that was much more algorithmic. But from my perspective, I think a lot about what are the access patterns and what are the forms of communication they need. For example, another really key example is what sort of because my box has many FPGAs in it, about 200 of them. Um, it's very relevant to me if somebody says, hey, look, my search can be phrased in terms of doing something parallel on everything and then a relatively small reduction at the end, or everything is, like I searched, a terabyte subset of a petabyte data set, and then each FPGA produced a megabyte of results, and then I aggregate them and give you an answer. Whereas if somebody says, no, I really need communication to answer my query, every single step of the process needs lots of communication, that's a very, very different sort of search application.
Okay, super interesting because you are giving me a perspective I don't get usually, which is related to hardware. And I am starting to hack on my own hardware, purely LLM driven. I've got my first, this is a replacement for Alexa. So I'm going to create my own version of Alexa with a voice AI. And so I'm learning a lot of things. And I've been in the technology world, which for the past 40 years outside of people like you who are actually like building the things, and this is why I'm really excited about all the questions I'm going to ask next, but like it's just been software. Like technology has been synonymous with software, and I know that the hardware does matter, but it hasn't mattered in a way until the AI is coming up, both because of the GPU crunch we were talking about, and now also I can build hardware. And so you said access point, and there's can you like what so access point or access pattern means that can you talk more about how the hardware like relates to search? Like what you're the so when I type in a search query, that is what's happening at the software level, but more importantly, what's happening at the hardware level.
Right. Yeah. This is a very reasonable question. So maybe I can draw it back to, I don't know how much you've played with sort of inference at home sorts of stacks, but they are very constrained by, in some sense, I'm a little bit generalizing here and drawing an analogy, but in some sense, the sort of data access patterns they need. So very typical sort of setup you'll have is you'll say, okay, I have a node, it has maybe 8 H200s in it, and they have super duper fast communication between them, either just peer-to-peer over PCIe, or maybe even an NVLink sort of thing. But then the moment I want to communicate from that node to the node one over, I might lose an order of magnitude in my bandwidth. I'm suddenly having to communicate over Ethernet or InfiniBand or something. And the application very much has to work around that. It has to see this hierarchy and say, okay, within a GPU, I have really, really high bandwidth. And if you zoom in even more, inside of that GPU, I have SMs, and each of those I've got, shared memory inside of that, even faster access. And then zooming out, okay, between the GPUs, I have this other speed. And then from one to the next, I have this, yet slower speed. And at some level, a lot of that is about matching the hardware and its communication abilities to the access patterns of the problem. And of course, these have co-evolved, right? So if we lived in a world in which it was easy to network, 10,000 GPUs, all with the bandwidth of NVLink, I'm sure that we would have, developed very different training algorithms. Maybe the need for ASGD and whatnot would have been a lot lower. But these things have co-evolved, and now they're like, very much entwined, right? You'll see a lot of stuff where people, sort of in the home inference space, are basically, not trying to do multi-node deployments because that's really obnoxious. And they're saying, okay, well, I'll scale my model up until the point where it, fits on one node and that's it, and stuff like that.
When does it get obnoxious? How many nodes?
Well, really having more than one node, having more than one node, you really are saying, okay, I have two separate Linux systems, and I have to do some sort of message passing, and one could turn off without the other, and whatnot.
So wait, a node. So in addition to the thing I just showed you, I got my Raspberry Pi, and I've learned recently that I can get that Raspberry Pi to network a bunch of old laptops that I'm going to buy, and then create my own personal server that can be a distributed system. Now that I believe that Raspberry Pi is a node, that is distributing all the computers together, and will balance based on usage. And this is all very, probably a bad explanation. Now, how does that compare to what you just talked about? Nodes of GPUs. Are you talking about one node within one GPU, or one node that is bringing all the GPUs together?
Yeah, by node, I sort of mean, speaking very informally, like that's just one computer. It's running one, Linux, and it's sitting there. And the reason that we sort of think of this is that, because that's a relatively useful abstraction for a thing that can fail by itself, right? I have my distributed system, is a whole bunch in your case, you've got your Raspberry Pi coordinating all those laptops. One of those laptops could, drop off the network all of a sudden. Now, of course, within a node, you can still have more fine-grained failures, right? It's anybody who's done anything at scale will have had the experience of, oh, only 7 of my 8 GPUs come up. So it's not to say that you can't have sort of intra-node failures, but for the most part, the reason why going from one node to multiple nodes becomes so complicated is that you now really do have this inescapable distributed system problem. Oh, okay, these guys have to communicate, they have to pass messages. One could disappear and the other one could stay up and whatnot.
So a distributed, and this is why people say distributed systems are really hard, right? Because as soon as you move from one computer to multiple computers, or one node to multiple nodes, that's when things get really tricky in terms of doing what? Why is that? Why is a distributed system tricky?
Right. Okay. So there's sort of two perspectives on this. There's the sort of distributed consensus, fault tolerance sort of world of stuff. And I will say, I think people sometimes lean on this too much. There's a great, okay. Let me go into a bit of this. If you talk about distributed systems, whoops, camera's falling over here. If you talk about distributed systems, people will love to tell you, oh, it's just completely impossible. You can't do everything. And they'll point to stuff like CAP theorem and whatnot. And say, well, you can't simultaneously be available and partition tolerant and also have a consistent view of the world. Um, and these things are true, but in some sense, they're overstating the difficulty sometimes. And here's why I'll say that. Um, in many circumstances, we actually, I should probably back up a little bit
Sure.
and
Yeah.
answer your question more directly and then get to my pet peeve about
Sure.
how people over invoke the cap theorem. Um, yeah, okay. Well, let me do this in a little bit more of a thought through order. So you're asking, why are these things fundamentally hard? Uh, the most extreme, they're basically hard depending on how much you want to model that things could go wrong. On one end, you could say, well, if any node goes down, I immediately stop and I try again. I'm like, oh crap, one of my computers crashed. Let me try again. If that's your world model, then probably distributed systems are not that hard, but you just have exponentially decreasing uptime in how many servers you have, right? Each server is up 99% of the time. You have 100 servers, you're going to be up 1 over E of the time. It's not going to be that great. Um, so that's one extreme. The other extreme is sort of like the Bitcoin style problem where you say,
Mhm.
I'm a distributed system and I don't even trust my nodes, right?
Oh,
That
interesting.
that is the extreme end of difficulty. So on one side, you say, I am just,
Yeah.
going to completely give up if anything goes wrong. And the other side, you're saying, I must never lose, even if people are trying to like take me down.
Mm.
And then in the middle, there's this broad range of sort of threat models may be a little bit the wrong term, but the broad range of what sorts of failures I'd like to tolerate and what sorts of availability I would like to have and what sorts of performance I'd like to have. And there are no-go theorems that say you can't achieve certain things. The CAP theorem
Mm.
was one of the famous ones, and it says, well, if you want to have a system that, is reaching distributed consensus about some fact about the world, and you can't simultaneously have the following 3 properties. You can't have it be the case that you're always available. You can always answer questions. You can't have it be the case that you always give consistent answers. And you can't have it be the case that you tolerate arbitrary partitions of your network. And people love to point to the CAP theorem and say, oh, well, you'd want to have all 3 of those. And I will say,
Oh, got it. Interesting.
I think they're usually overstating, in particular, the sort of availability requirement. Like, here's an example, is that the cap theorem also applies to your bank, for example, right?
Mm.
Your bank is a distributed consensus-y thing, right? You can go to branch A and ask for your balance. You can go to an ATM and ask for your balance, right? And they all want to agree and tell you the same amount of money in your bank, and they don't want to make mistakes and let you overdraw. You shouldn't be able to go to your ATM, withdraw your last $100, run over to the teller, and also withdraw that last $100, right? It is the case that your bank is supposed to be like, somewhat partition tolerant, right? Like sometimes, maybe the ATM will lose its network connection. And they want pretty good availability, right? Like they want it to be the case that, when you go to the ATM, usually it's working. And in practice, it's not the case that like the cap theorem means that banks don't work, right? Like, in
Interesting.
practice, you just give up a little bit on availability, and every so often the bank reports, "Oh crap, I'm having trouble contacting the network. Oh no, wait, I got them again. We're good." So, um, I
Uh,
like yeah, I don't want to understate it. There are probably some people
yeah.
who are going to listen to this podcast who do distributed systems. Distributed systems are incredibly hard. It's a huge active area of research. People are coming up with all sorts of crazy algorithms, and they're like, "Oh, I've done my fast Paxos, and I've removed a round trip from this communication scheme, and I've done this. I've done like they're doing amazing work. I'm not trying to minimize that at all. Sorry, I'm a little bit responding to a thing you didn't say, but a pet peeve of mine, which is I see people on Twitter say, you can't do that. Distributed systems, blah, blah, blah theorem says it's impossible. And it's like, well, yeah, because the theorem required an incredibly strong notion of X, Y, and Z. And if you weaken any of those a little bit, the theorem does. I'm a little bit doing a hobby horse of mine.
Yeah.
I'm a little bit rambling at this point.
So I got a very important understanding about technology from what you said, which is that the bank is there's a statement of a record, or there's a record, and this goes back to what I was talking about the ledgers. The huge innovation with the Medici's was they figured out a system, a knowledge management system, to have a record that everybody could agree on, so that if you could withdraw money, you go to Paris and you withdraw money, and then they manage that record behind the scenes. Then in the 1960s or 1970s or wherever, there was a time period where people started to build databases, and those databases, the relational database, I believe, was where, a company could agree, like you said, where a bank basically has this ability to allow you to take out money, and then you can't go to the teller and then have take out the same amount of money that you just took out. So it's like, and then that's what distributed systems are doing. It's a really like it feels really simple. The Medici's they created this record that everybody was able to see and agree on, and that was a huge innovation that sort of underled the entire financial revolution, industrial revolution, scientific revolution. And then in the 60s, 1950s. Actually, do you know when the first database was
No, I don't
was
know. That's a good question.
yeah. And I've been going into the knowledge manager, like how did they organize all of their folders into files in the 1960s, and it turns out there's all these crazy innovations that they have actually like physical filing, but that all got abstracted into the computer that we're now interfacing with right now, and it's all just behind the scenes. This is why I love talking to people like you who are basically not only doing the database stuff but also doing it in the hardware. And I guess we can go back to that too, because it's like fundamentally everything that there's all these abstractions in the way. I'm slowly starting to understand some of these abstractions, but in the end, it's all just zeros and ones on a computer that are allowing for an input and an output. And so let's go back to the FPGAs. So we've got these FPGAs, and for some reason, you are doing search applications, and so you need to basically search a bunch of machines to get the information. And the FPGA does that because it basically allows you to do what? What does the FPGA allow you to do there?
Yeah. So one perspective that's a little bit glib is just FPGAs are a particularly cheap way to buy DRAM controllers and NVMe controllers, or not controllers, but interfaces. So I'm kind of using them as I/O expanders. So I say, okay, I have a box. I'm just going to fill it with FPGAs. Each of those FPGAs is going to talk to, some DRAM and some flash. And there are a bunch of people who have built architectures kind of like this. There are many all-flash arrays on the market. One property of a lot of them, though, is that they tend to throw away a lot of the bandwidth that they have to their flash and to their DRAM the moment they have a PCIe link to the host system. So, you have your host system, it might have, I don't know, 100, 200 gigabytes a second of bandwidth over PCIe to a bunch of FPGAs. Well, those FPGAs, if you multiply it out, probably have a lot more bandwidth than that to their DRAM and flash. So if you can move a little bit of your application closer to the actual storage, put it on the FPGAs, the search application,
Yeah.
you can potentially speed things up a fair bit. Now, there are a whole bunch of, I'm sure that any listener who's sort of familiar with the sort of storage space already has various things going off in their head where there have been many efforts to do sort of smart storage. And this is like there's a long history of companies that have tried to do something like this. I think we're a little bit different from a whole bunch of these in how general and what we're giving people is. So it's not like, okay, you run a tiny little program on the like some NVMe controller or something, right? There are various smart storage drives that are trying to do that. We're trying to say, no, we're like devoting actually pretty serious programmable logic resources and pretty serious DRAM to every single node in this FPGA array. I think that's sort of a partial answer to what you're saying.
Yeah, no, I got it. And this gave me another sort of understanding, a little tiny understanding of what's going on. The programmable logic, because that's in my studies what an FPGA actually is. And most of this comes from robotics. I feel like a lot of people are using FPGAs in robotics, and I think you gave me an answer when we first started of why, which is that they just have a lot of input and output of like sensors, of giant sensors that are assuming to do it. What, like, can you, bro? Yeah, can you burrow into that programmable logic? Because I know about logic in terms of the if and statements, all these sort of programming things that you can do in the software. But why is it important to have that in the hardware?
Yeah. So FPGAs are an interesting trade-off where, so in the extreme end, I mean, if you want to view them as like crappy ASICs, so I guess how familiar you are, I'm not sure where I should start, either for you or for your listeners. Okay, so
I
if you
do.
want to get
Yeah, go for it.
go ahead.
So
want to
a
get it.
crappy ASIC is basically a crappy ASIC. I know that they were Bitcoin mining, and they were not customized, right? A GPU can be customized; it's generalizable. ASIC is specific, not customized, or
Yeah, yeah. So Bitcoin miners were one example use of ASICs. So ASIC, application-specific integrated circuit. The idea is you've made a custom chip. You've actually, in the silicon there, configured all of the FETs to do the logic that you need done. Maybe it's for Bitcoin mining, or it's for some networking thing, or it's for computing some specific thing. Like, oh, I have an ML ASIC and it can do these flops very efficiently. Now, getting ASICs made is extremely expensive. The IP and tools can easily run you millions of dollars. Mask sets can be, tens of millions, and they can take, you could have 3, 4, 5 month lead times to figure out if your design worked. So these are extremely expensive projects. And a question that people have had, now for 40, 50 years is, can we in some way make it so you can at least prototype and get some fraction of the performance of an ASIC at a much, much lower cost? And in 1985, I think it was, Xilinx there were other programmable logic approaches before that, and things where you'd have, you know, configurable FETs and you could wire them up in various ways. But Xilinx was sort of introducing, okay, let's do these arrays of lookup tables to make an FPGA that sort of emulates an ASIC. And the way that FPGAs work is actually pretty different from what's going on inside of an actual chip. An actual chip, everybody loves to talk in terms of logic gates and NAND gates and whatnot. The real thing that's going on there is you kind of only have two components. You have NFETs and PFETs. So you have these two kinds of switches, and they're put together into these things that are called standard cells. And then there'll be these tools that will say, okay, I've mapped your design, which is in some hardware description language. I've done what's called technology mapping. I've turned it into a bunch of, standard cells, or, and those things might be pretty simple logical things, or they might be more complicated. They might have a little bit of storage, like it's a flip-flop. They'll map it into that. And then they'll place all of them and they'll route them together. And then ultimately all of those things are made of FETs, these two kinds of FETs I've mentioned. And then finally it just becomes rectangles in a GDS2 file. And that gets shipped off to Taiwan. They make you the thing and then it comes back. But as I mentioned, that's extremely expensive. And FPGAs approach it pretty differently. FPGAs say our fundamental building block, and stop me if I'm going too quickly, but fundamental building block in an FPGA is an n-bit to 1-bit lookup table. It turns out that you can implement this quite efficiently in hardware. You can make little reprogrammable lookup tables. So for example, with Xilinx, they're all 6-bit to 1-bit. So you'll say, okay, I'm going to give you a grid of 100,000 lookup tables, each of which has 6 input bits and 1 output bit. And it can do any, operation you want on that. They're, 2 to the 64 such possible things, and you'll program each one to do what it wants. And then there'll be some reconfigurable routing, which actually turns out to be where most of the, a lot of the difficulty actually is. The routing and the, I'm going to say some words that will mean something to some of your audience, but not the rest. That's where a lot of your propagation delay comes from, actually. The majority is usually from the routing. So that's where a lot of the cost is, but people sometimes don't focus on it as much. They'll have this reconfigurable routing fabric on top where they'll say, okay, I have this lookup table and its output I want to route into this guy over here. So I'm going to turn on this buffer that'll read the output here and write it to this little physical piece of metal here. And then that physical piece of metal will span somewhere. And then I'll pick it up with another little buffer that'll read it and write it here, and so on. And you configure everything just right. And then this huge grid of lookup tables and a bunch of other stuff, carry chains and whatever, will act like it is that ASIC design, or it'll act like it's your RTL design. So and the performance characteristics, the ratios aren't exactly the same. An immediate question you might say is, hey, wait a moment. Before I was taking my hardware design and mapping it into these standard cells. Now I'm mapping it into lookup tables. Will everything sort of be 1-to-1? Will I be like getting the same thing, but 5% of the speed? And the answer is no. Not everything is the same cost. Some things are like the landscape has shifted a little bit. Some things are more expensive than they quote unquote should be, and some things are a little bit cheaper than they should be on FPGA. But it turns out to be, close enough of a matching, and the tooling is similar enough, and the design problem is similar enough that you could sort of think of them as crappy ASICs. Now, that ratio of how crappy they are by can be enormous. I mean, if you can't if you have an application that is not, taking advantage of some specific hardware block
Mm,
in the
mm,
FPGA to do some of the hard parts, uh, you know, you could easily be saying, okay, I have 1% of the performance or something, at which point you might ask, why am I doing this at all? Maybe I should be trying to map my application to a GPU or a CPU. And this is why I was getting back to at the top of the show, why I think a lot of people end up being pretty disappointed by FPGAs. They're much more niche than a lot of people think. Like,
mm.
an example that I point to a lot, and again, stop me if I'm rambling too much, but I think this is really illustrative. If you look at Xilinx, the number one FPGA manufacturer in the world, and you look at one of their highest end parts, if you go on DigiKey, this part costs $100,000, the VU19P, and they advertise it as being this like absolute beast. They're like, we can do 500 gigabytes a second of memory bandwidth on this. And you think 500 gigabytes a second? That's like a mid-tier GPU. Like if I go to Best Buy and buy a $600 gaming GPU, I get the same amount of bandwidth. And it's just true. Like it is actually the case that FPGAs, unless you have some really, really specific reason why you need to use them, like you're an HFT guy, or you need the IO expansion, or you need to talk to a lot of things, or you have some really low latency radar application or something. On every other sort of metric, you'll probably be beaten by another system. It's very interesting. And this is a misconception I run into a lot. People think, oh, FPGA, you could probably do crazy flops. And I think, oh, no, no, no. This is like, anyway, I'm a little bit
Yeah.
rambling.
So, really interesting stuff. I really like the metaphor of a crappy ASIC, but it allows you, instead of going to Taiwan, so basically it's a way to prototype your ideas without having to go get them put into literal metal, right? Like you
That's
can't
right.
act.
That's right.
Okay. And then performance, and there's only these very niche applications. And you said systems. You said like a GPU. Well, why don't you could just go get a gaming GPU to go do the thing that you're trying to do. How many? And then you said you could burn it into a CPU. I get so FPGAs, GPU, CPU. Those are the systems, right? Are there other like what are the other potential systems that you could use in this computing landscape?
Yeah, it's a very reasonable question, right? I mean, for a very long time, basically the only game in town was
Mm.
CPUs, x86 CPUs. It's like, okay, I'm a big company, I've got some big data intensive workload. I'm going to figure out how to run it on some fleet of servers. And for a long time, this is what everybody did. And then it has started being the case in the last, decade or two that people have found, wow, these gaming GPUs, as their pipelines have gotten more programmable, which is initially for graphics, right? The point was, I
Got
want
it.
to write my fragment shaders, I want to write my vertex shaders and have that be programmable. People started doing so-called GPU, which is the sort of general purpose computing with GPUs.
Mm-hmm.
And then people started to find, wow, these are very, useful. If you have an application that fits
Mm-hmm.
well onto their their sort of model of how computation can be done, they give you insane memory bandwidth and they give you really high flops. And then, of course, that catalyzed some of the ML craze that we're in right now. Um, as people have seen the success of GPUs, of course, the immediate question, and everybody else's, is the great question you just asked, right? Like, you thought, well, I see CPU, I see GPU, I see these ASICs. What else is there? 100,000 other, well, maybe 100,000 is too high, but a gajillion other people thought,
There's
what
one.
is the next
Okay.
thing?
Yeah.
So lots of people have been trying to make various accelerators for various things. Programmable networking is one that some people have sort of focused on, saying like, oh, okay, I'm going to, have some sort of switch and I'm going to run a non-trivial amount of my packet filtering inside of some switch. And I mean, I'm describing niche things, but these are things that
Yeah.
people actually do. Um,
Yeah.
there are a gajillion accelerators for all sorts of, applications. Now, of course, ML accelerators are huge. Everybody and their aunt has one, like you constantly hear of one and you think, how have I never heard of this? And you look them up and they have, $500 million of funding, right? Like, so, um,
Yeah.
there are a
Interesting.
ton of people. I've talked to people who are doing cryptography ASICs and accelerators for all sorts of stuff. It's a little bit hard to know how to answer your question, in part
Super
because
on.
it's very broad. And also there's like a long tail of decreasingly programmable, increasingly specialized hardware. Um, So
Yeah, interesting. Because that's what it is the different. Oh, and this goes into Makimoto's wave. I had a great podcast guest probably about 9 months ago, who was a former NVIDIA guy, and he was telling me about
very cool.
Makimoto's wave, where they basically go in between customization and specialization. And his theory is that the GP we've now got our customization, so now we're going to go into the specialization. And I'm sure he was like working on those ML workloads. So, and that brings to mind the question that's been coming back to me a bunch: is are there any like we've been talking about you're using FPGAs for search, and we're talking about vectorized database, so that's one right there. But do you think FPGAs open up anything in terms of that sort of GPU kind of surprise that, oh, we can use GPU for machine learning? Are there any other sort of AI applications for FPGAs that you see coming online?
So certainly every FPGA vendor is loves
Trying.
to say that exactly that is coming. I was Xilinx and Altera, they're all saying, "Oh my God, use our stuff for," and I think there's some of that that will be possible, especially because I think it's funny. I want to touch on something you said before, which I think
Sure.
is very important, which is the special, and then I'll get back to what you just asked. One history that you could see in every single field, or sort of thing in computing, which is so interesting, is each thing starts specialized,
Yeah.
slowly becomes more general, and then eventually gets leapfrogged by the person who says, "Oh, I didn't need all that generality. Let me specialize." CPUs are kind of an example of this. They start very specific, and then people say, "Oh, okay, I could add more programmability, and I could eventually make them, into this general purpose thing." And then somebody says, "Well, actually, I just want graphics. I just want to run this very simple fixed function raster pipeline." And then the next person says, "Oh, I really would like a little bit of lighting here. Okay, I want like a little bit like N64 style. I want a little bit of programmable microcode. I can tweak things around the edges." And the next person says, "Actually, do you mind running just like slightly more code for me?" And then suddenly you have this like programmable, like shader engine. And then somebody else says, "Well, if you drop some of the raster stuff and just beef that up a little bit, then that's actually a pretty good computer." And then the next person says, "Oh, you've gotten too general. I want to specialize again." And then they make the TPU. And you can see the exact same thing happening with Google's TPUs, right? The first generation TPU was this like comparatively simple systolic array that could not do that many different things. And then they say, "Okay, let's add a little bit more programmability. Let's add a little bit more programmability to it." Okay. And now like the TPU V4 or whatever they're up to is like a very programmable thing. So has, big systolic arrays in it. And then the next person comes along and says, "Oh, no, 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 no. It turns out all that generality you added, I just want to do transformers. Let me like specialize again." And like, this is the history. And like, I'm sure it's going to happen, right? Like Etched is saying, throw away all that generality. We just want to do transformers. And I don't know them. I don't know their stuff. I mean, I know a few people at Etched, but I would be
Yeah.
shocked if they did not do the same exact trajectory of for V2. They have customers who say, "Hey, could you put in a little bit of programmability here? Could you put in a little bit of programmability there?" And then eventually the next person says, "Screw all that. Let's make an even more specialized thing." So everything is just sort of like this constant treadmill of each thing becomes more and more general and then gets leapfrogged by the specialization. So that's one pattern that I think is key to look out for. Now, you were asking about FPGAs opening
Yeah.
up something in AI. Uh, I a little bit think that somehow, uh, if anything, FPGAs are maybe kind of doing the reverse. Like they are putting in increasingly putting in hard IP blocks that are sort of specialized for AI. They say really just sort of more DSP resources.
IP as in intellectual property or something else?
Yes, yes. It's very strange. The hardware world calls things
Oh,
that programming software people would call like libraries and functions. They tend to call a lot of those things sort of like IP. They'll be like, "Well, I use this IP block," whereas a, a software person would say, "Oh, I use a library." It's just a terminology thing.
got it. Okay, got it.
So they're putting in actual hardware. So let me back
Yeah.
up for a second. Um, One of the things that FPGAs do is as a concession to the fact that they are playing on at such a disadvantage is that they're going to say, "Okay, there are certain sorts of things that you will typically want to do where if you build them out of those lookup tables I described, it's just too big of a cost and they're too common. So we're going to build in specialized hardware." Addition and multiplication are two of the big ones. They tend to have these things called carry chains all over them so that these random lookup tables can be assembled to make adders. And they also typically will scatter throughout throughout the fabric a handful of multipliers, just big integer multipliers. And they'll say, okay, whatever you want to do, we can probably, whatever arithmetic you want to do, we can probably, with the right sort of padding and shifting and whatnot, map it down onto these resources. And immediate thing you can then say is, if I want an FPGA that's especially tuned for running some sort of AI workload, now I will separately say I think I'm somewhat skeptical of this as an idea, but if you wanted that, which of course these manufacturers very much do, you could just turn those knobs. You can say, well, I have a certain amount of area, and was previously putting down, I'm making up this number, but like I put down 1 multiplier for every 1,000 lookup tables I have. Now I'm going to put down 1 multiplier for every 20 lookup tables you have. Give you just way more multipliers. Or maybe I'll even go more specialized than multiplier and make it be an actual FPU or something that can actually,
FPU?
know how to do the a floating point processing unit.
Is that like a GPU, or is it a name that's
great.
me?
Great question. Yes. I could totally see how that name would be a mismatch.
Yeah.
Despite the fact that it still has processing unit at the end, rather than being like a discrete piece of hardware, FPU means like a really tiny specialized circuit within a chip that just does floating point operations.
Oh, man, I'm excited for the next 5 to 10 years where I can kind of, because it doesn't feel like I understand the software side of computers at all yet, but I have a much better understanding of what's going on in the software than I do with a lot of the things you just said. The thing that comes to mind is the fabric. You said fabric. Does that mean scatter throughout the fabric? Does that mean like the metal fabric or the semiconductor fabric, or is it something else?
Kind of, yeah. I mean, so the routing fabric is this big reconfigurable set of switches, basically. You think of it as of saying, look, if I want to be able to connect up anything to anything, then I'm going to have a bunch of these different connections, and I'm going to be able to say, turn them on and off. Like, sort of, it's, depending on the FPGA architecture, there are a bunch of details on the lighting that some of your listeners will be aware of, but you could think of it as being like, I already physically had this wire, I already physically had this wire, and when they cross, I can optionally say, hook them up.
Got it.
And that's kind of what we mean by the fabric. And because routing is such a large expense and is a huge limiting factor on the speed at which you can run these designs, actually, this is sort of the propagation delay thing I was talking about earlier, how things are spatially laid out inside of the FPGA matters quite a bit. So you don't want to just like put all your multipliers at the bottom, right? Because then you'd be like, okay, I have my design up here. Oh, once I get some multiplication done, it has to route some stuff to be long wires down to the bottom, get the multiplication done, and route it back up. You really do want to spread things out in there internally so that wherever you're doing your processing, you have a multiplier nearby, I'm speaking in very rough terms, but
routing fabric. So we'll take like 5 to 10 more minutes. If you have to go at the hour, let me know. But routing, is this the same type of route? Is it basically the same thing as network routing on a specific FPGA or another, or a GPU or a CPU? Like, how is routing different inside of a hardware versus inside of a network?
Right, super reasonable question. It's different in that it's done statically, right? So in an FPGA, you say, look, I have these, 50,000 lookup tables I need to hook up. Put them somewhere where they can actually be, allocate actual physical lookup tables to be my logical lookup tables. And then I need to statically figure out which wires I'm going to use to hook things up. In a network, a packet switch network, it's more like you look at the address and you figure out where you want to go and you send it somewhere. Now, of course, there are things that can sort of act like that packet switch network on a chip. Sometimes people talk about network on a chip as a sort of design paradigm where you say, hey, look, I want to have these things that communicate, and rather than having dedicated wires, they're actually going to have a packet switch network internally and be able to say, hey, please send my message to Bob, and then, send it to some sort of internal routing mechanism. So there are commonalities, but I do want to be clear that when I'm talking about routing here, it's like a sort of static problem of drawing the city map and figuring out where, all the roads are going to go. Not doing the delivering of a letter, which is more looking at the address and, figuring out where to go.
Got it. Interesting. Okay. So yeah, last few minutes. What are you most excited about in terms of the business side of what you're doing? What, you got the hardware, you're hacking on the hardware. What's the either the most exciting or the thing that you're trying to figure out right now?
Well, so the main thing is that in the very near future, I expect to we're currently putting together this prototype. We have a bunch of prototype boards. We're doing lots of bring up on them. Anybody who's done hardware knows how grueling that can unfortunately be. But things are going great, and hopefully we should be ready pretty soon, ideally like January, to start really doing some demo applications and sort of POCs for potential customers. So the thing I'm most excited about is just to have people come to me with their problem. The main thing is that we're offering to people, we'll write all the obnoxious Verilog, we'll write all the gateware. You just give us a sort of software interface that you would like. You say, okay, I would like you to accelerate this application. I'd like to accelerate these sorts of operations. We'll write that for you. And then I'd love to just work with people,
Wow.
see how much we can speed them up. I'm doing one demo for a vector database company. I don't know if I haven't asked them if I could say who they are, so I'll just be on the safe side.
Yeah.
And it's very exciting. They're like, hey, please implement these through these, 3 or 4 functions, and let's see how many queries per second you can do. And I just love tasks like that, because then it's so good to be able to, really get my hands dirty and, sit down for a day and get the number 5% higher or whatever it is, And
So
the next day, 5% the next day.
for the people listening, so vectorized database companies, any other kind of specific companies where you want to get the word out for them?
Absolutely. Yeah. Thanks for doing my job for me. You should do the plug. Search vector databases, I think, are really great applications, large, sparse things. We were talking to some potential people doing streaming applications, some people who are doing sort of network security sorts of things, and some people had some very interesting, like, well, I won't get too much into it. We're also looking a little bit at sort of ultra-long context attention applications. I think there are potentially some sort of disaggregated attention applications. If somebody's working on any of that stuff, totally feel free to reach out to me. Or even if just, you're interested in chatting, because we're doing search and vector databases right now because we're a really, really good fit for that. But that's not the only thing we can do by any means.
Very
large data intensive stuff. Yeah.
Large data intensive stuff. Okay. I have a few people who come to mind. Okay, cool. Thank you so much. And how are you writing? I know you did a great Twitter video on this, which is the reason we're doing this show. Are on Twitter, anywhere else? What is your Twitter?
My Twitter is my name with no vowels. It's a terrible handle. So it's PTRSCHMDTNLSN, which is kind of awful. But if you search for Peter Schmidt Nielsen on Twitter, you'll probably get me. You can also find me, I'm Peter@SaturnData.com. So it's a pretty easy way to reach out. Yeah, and I'd love to chat with anybody.